Hello, I'm Austin Henley from the University of Tennessee, and today I'll be sharing our idea for an inquisitive code editor that helps novice programmers overcome misconceptions about their program's behavior. I'll start with an example of a bug that an actual student submitted as part of their homework. The program asked the user to input Y for yes or N for no, and it will repeat until valid input is given. However, the loop will actually never end because of a mistake. The or should instead be an and. These types of mistakes are known as semantic errors. It compiles, but it does not behave the way in which the programmer expects. And program correctness is particularly challenging for novices because they have a different definition of correctness than professional programmers do, according to one study. In fact, another study reported that students believe their code is correct when there are no more compiler errors. Due to this flawed definition of correctness, semantic errors persist and take far longer to fix than syntax errors. So if we look at these mistakes in more detail, both syntax and semantic errors are common, but syntax errors are often fixed quite quickly. Unbalanced parentheses are the most common type of syntax error, according to the black box dataset, and they take about 17 seconds to fix on average. There's been a lot of research characterizing which syntax errors that novices make, as well as solutions to some of these problems. One solution is enhanced compiler error messages, which help programmers locate and shows them how to fix syntax errors more efficiently. There's also block-based languages, such as Scratch, which can eliminate most, if not all, syntax errors. For semantic errors, the most common one, according to a study, is calling a function but ignoring the return value, such as toString in Java. This semantic error took students 50 times longer to fix than the unbalanced parentheses issue, if they ever fixed it at all. Researchers have proposed that the cause of these semantic errors comes from a lack of conceptual knowledge or inadequate problem-solving strategies. But ultimately, the novice has some misconception about how their program will behave, and it takes considerable effort for them to realize that they even have a misconception. So when I was looking into these misconceptions, I was really inspired by the YLine. YLine was Amy Coe's dissertation project that enables programmers to ask why and why not questions about their program's output. It provides these features by recording a program execution and using dynamic slicing to map the output that's in question by the programmer to the sequence of code that caused the output. And although YLine is fantastic for helping experienced programmers in tracking down their bugs, it may not help novices with semantic errors, since they often aren't even aware that they have a bug in the first place. Which led us to our idea. And this idea that we're proposing is an inquisitive code editor. Rather than the programmer asking questions, it is the code editor asking the programmer the questions. It works in four main steps. First, the code editor detects potentially problematic code, meaning code that will compile but correlates with semantic errors that novices have. Second, the editor will ask the programmer a question about how they think their code will behave. And third, if the answer is different than how the program will actually behave, then the tool can attempt to correct the misconception, as well as assist in fixing the buggy code. And finally, the editor can try to prevent future misconceptions of that same type. So looking in more detail of each of these steps, there's a number of existing techniques that we are using to identify these potential semantic errors. For example, there are data sets of common mistakes that novices make, and we can plug that that set of potential mistakes into existing code smell detectors. We can also use static program analysis to know when code can never be reached or if a loop will never iterate, since those are likely to be mistakes by the programmer. and actually happen quite often by novices. To expand these types of potential errors and to generalize to several different programming languages, one of the students working with me on this project is training machine learning models to identify new code patterns that correlate with bugs. Now, inside the code editor itself, the tool will annotate the potential problems with a question mark, as seen in this screenshot. And we want to entice the programmer to click it, but not be too disruptive. So we're using prior work on negotiable interruptions and a concept known as surprise, explain, reward to get them to click these. Now, once they do click the question mark, the editor will show them a question from a predefined set of questions. In this example, there is a for loop that iterates on a list, but the list is either always empty or only has one element. So it's fairly pointless to do a for loop. In this case, the tool can ask them to enter a range of how many times they believe that the loop will iterate. If they answer more than one time, then the tool is confident that it has identified a semantic error and that the novice has a misconception about how their program will behave. And so if they did indeed answer incorrectly, then this is an opportunity to teach them about how the program will actually behave and how to potentially fix it. So the tool can provide an explanation and also point them to the relevant bits of code that will need to be changed. Although in some cases we could automatically fix the error that's in question, the tool will actually only provide support in making the fix, since the goal here is for the students to learn how to do it. And not only that, but the tool can also prevent future misconceptions. One study found that particular errors happen repeatedly to students, even in the same coding session, and it could happen 6, 7, 8 times in that same session. So since we have already elicited the expected behavior from the programmer, the tool can generate test code in the form of assertions or unit tests, as well as generate documentation in the form of code comments. That way, if the behavior ever deviates from their expectation again, it will provide a clear signal to the programmer that something's wrong. Additionally, the tool can monitor issues that reoccur and suggest tutorials or provide longer explanations about that error. The tool can also provide aggregated reports to the instructor about common issues that their students are having, and those can be referenced in future lectures or office hours. So far, our tool is implemented as multiple Atom plugins that we are actively working on. We're also training several different predictive models for identifying problematic code, and we found some promising indicators of this type of problematic semantic errors. Not only do we use the code as input to the models, but we also use the programmer's behavior and events from the code editor, such as adding or removing print statements, breakpoints, or editing the same line of code repeatedly. Those could be indicative of the programmer having an issue in that region of code, but not quite knowing how to fix it. We're also exploring what questions should the tool even ask and what information is most beneficial to be provided as part of the explanation. We're also trying out different interaction designs that minimize the interruptions and false positives, yet still entice the programmer to click the question marks and answer the questions. So after we evaluate each of these components individually, we plan to put them together and to conduct a lab study and longitudinal study of the entire system. So just to summarize, we proposed an idea that we're actively working on for an inquisitive code editor that identifies, corrects, and prevents misconceptions that novices have about program behavior while using research from program analysis and tutoring systems. Thank you.
All right, we are on air, and welcome everyone. So this is the Q&A session for Austin's paper on an inquisitive code editor for addressing novice programmers' misconceptions of program behavior. So this is an idea paper, and Austin is with me to answer your questions and comments. So shoot.
Ask me anything.
Ask him anything or comment on the idea. Okay, so maybe I can get the ball rolling a little bit here. I am wondering, Austin, whether you will be relying on things like static analyzers as well as an adjunct.
Yeah. So I have several students kind of working on the different components of the code editor. And so, yes, one student is actually trying to use just off-the-shelf static analysis methods to identify certain anti-patterns in code. So he's taken from the literature some set of common patterns, anti-patterns that students face when writing their code, and he's just plugged those into an existing analyzer. And so that way he can work on the later components of the editor, like the feedback that they get or the explanation part. But then on the flip side of that, I have a student that is trying to identify more patterns, more of these anti-patterns. And so he's using some machine learning as techniques to further what kind of patterns we can plug into the static analyzers. So those are identifying the potential misconceptions that students have, such that we can do the explanation aspect of it after that.
So are you going to be looking into also things like kind of violation of coding practices like clean code and stuff of that sort, not just bugs, but potentially harmful patterns as well?
We've talked about it a bit. So at the moment, we're focusing on like introductory computer science students, at like CS1, CS2 level. So
I see.
First year, second year students. So we've talked about applying this to professional developers as well. But so for the CS1 students, I would not want to go the clean code route, just because they're still trying to get that while loop.
Yes. Point well taken.
Yeah, but for the professionals, yes. So there's a lot. We were trying to go towards getting them to elicit documentation about complex code. So if we can identify the components of their code that they're writing that are inherently complex or interesting, then we can try to ask them like, hey, there's actually no documentation, there's no code comments. Can you elaborate on an explanation? And so we can pose questions to kind of kick off that. Yeah.
I see. We have one question from Marianne, and he's asking, can you say a bit about the limitations? Are there kinds of defects that you will not be able to consider?
The biggest limitation is that we're trying to find these misconceptions, as I'm calling them, and so the limitation is in the person's head, and so they're finding these defects is not like a binary yes no. There's no quantitative or objective way to just identify it. So we're having to go at it from different angles to find kind of proxies for these misconceptions or these logical bugs. So are there certain kinds of defects? Yeah. They're essentially all of them are potentially difficult to get to, and we're just trying to get at them from different ways. So at the moment, or the first step that we went through was to use the existing literature on the black box data set, which is a huge data set, I think from the University of Kent, on Java novice developers. So it has all of their code changes. It has when it compiles, when it doesn't compile. Some of the data even has unit tests. And so we're able to use that to look at the very common issues that these introductory computer science students are facing. But because these are not syntax errors, these are semantic errors and misconceptions in the person's head, we're really just trying to find correlations that lead to that misconception. So there's all sorts of limitations.
I see. I'm wondering about whether you imagine this to be wholly automated, or is there a place for guided feedback like system flags, potentially problematic regions, and instructor approves the true positives and then customizes the questions to be presented to the student? Some element of back and forth or approval process with the instructor.
that's a really good idea. And actually, so there's the feedback loop with the student while they're in the code editor. But I don't know how much of it I went into the paper, but there's also like the aspect that generates a report for the instructor. Like, here's a weekly report of the common issues that your students are facing. And so then they can try to involve that into their office hours or lectures. But what you're making me think is that there could be some kind of feedback loop where the instructor gets some information, and then they can change what smell detection is on or what flags the system is using. And so the next day, when the student goes back to their homework to work on their homework, they're getting different feedback based on what the instructor was able to see. Yeah, I think that's a really good idea. I think the instructor does need to be involved, and it's not just like let's train this model once and be done with it. It's this continuous loop. Yeah.
Right. And actually, if you're using machine learning, and then you can use that feedback to be able to retrain incrementally the models as well.
Yep, definitely. It's a good idea.
All right. I can say really, really great work. I think it sounds very, very promising. We have another question from Elke. What is your opinion on including style deficiencies or efficiency issues too?
Mm-hmm. Yeah. One of my students, they really wanted to work on that. Kind of like what I mentioned earlier, for the introductory students, they're just having so many issues just getting their code to compile or to behave in any way similar to what they're wanting to complete their homeworks. I really don't know. It begs the question of, should we be trying to teach them the basics of like style and good code from the very beginning, so freshmen, first semester students, or whether that should wait? I don't have a good answer on that. I think there's definitely some room for it, but the students that I've kind of like put our prototypes in front of, they're just struggling with the getting their for loop written at all. So I'm not really sure how much feedback we can give them on style yet. They might get mad at the tool or something. I'm not sure.
Yeah, this goes back to kind of what I asked earlier about, clean code and stuff like that. Maybe that's too much when they're trying to figure out just the basic logic of programming constructs.
Yeah, but there might be some subset of the clean code that's appropriate for these introductory students that could, really, really help them, because they just getting them to indent their code, I don't even think about it, right? But it's something that we have to actually teach them. So I think there's room for the tool.
All right. Okay. Thank you very much. We have another minute to go. I don't see anything else, but maybe we can give it a little bit of a break, just 30 seconds breather for you. And then you can join the discussion group. Okay, so thank you, Austin. So let's give it up virtually for Austin. And please feel free to join him in the discussion room in about a half a minute.
Thank you very much, and thanks for the questions.
All right. I'm going to leave the room right now and go to a different session. So please stay here until the prompt for joining the discussion group pops up. Okay, thanks everyone.